Hello, and welcome to this fifth of six films about the high-level energetics topic. We're nearing the end now, and because it was starting to get quite dark behind me compared to in front of me, I was starting to glow a bit too much, so the lights are on for the end of this series. Hopefully by the end of this film, you'll understand in simple terms what we mean by entropy, and you'll be able to identify changes that take place that involve changes in entropy and whether the changes will be positive or negative. And furthermore, you'll be able to calculate an entropy change for a particular process if you're given standard entropies. Okay, so in an attempt to try and explain entropy in a very, very simple way, I'm going to tell you that the universe, which started off as everything squashed into a very, very small space and has been sort of went bang in a big way and has been expanding ever since, is heading for a state where the energy in the universe is dispersed in a more disordered form. Now, to cut a long story short, everything wants to be as disordered as possible, would be a kind of simple way of thinking of it. And if you're ordered, it means your entropy is small, and if you're in a disordered state, it means you've got a higher entropy than you would if you were ordered. Okay, so your entropy is large. And the entropy of the universe is increasing, in other words, as it becomes more disordered. Okay, so changes in entropy, so delta S, is a positive quantity when the entropy increases, or in other words, when things become more disordered. And vice versa, of course. Okay, so if we try and recognize disorder in systems, in chemical systems, we might consider how the particles are arranged for a start. Okay, because we don't really need to go down the energy road with disorder in the higher level energetics topic. Okay, but we do need to be able to think about how ordered particles are. Now, this first thing here, this picture of the word entropy, is showing the particles starting off in a very ordered state and becoming more and more disordered. Okay, so in other words, the entropy of this system is increasing as we read the word, I suppose you could say. Okay, here we've got ice, right? And in ice, all the water molecules are arranged in very neat forms. This, I think, is supposed to be some kind of snowflake pattern. And when they're ordered, their entropy is low. When they melt and become water, so they're starting to move around more and they're not confined to this ordered arrangement, they become more disordered and their entropy is increased. So delta S is greater than 0. Okay? Try and ignore these entropy changes here. I didn't notice those when I copied and pasted the diagram. If we've got a substance that's dissolving in a solvent, okay, in the state that things are in before it dissolves, we've got all the solvent particles in one place and all the solute particles in another. By the time we've dissolved the thing, they're all spread together. They're not as ordered as they used to be. So dissolving things also leads to an increase in entropy. Okay? Now, if we want to try and answer the type of questions that we're going to get in an IB exam, we need to be able to spot when disorder is arising, or when it's increasing or when it's decreasing. Okay, so increasing entropy will always, or an increase in entropy will always accompany an increase in particle movement. So if you heat something up and the particles start vibrating more violently and moving around more, you'll be increasing the entropy of something. If you cool it down, you'll be decreasing its entropy. If you change a state, okay, so if you go from a solid where everything's neatly ordered to a liquid where it's all jumbled up, or to a gas where everything's just moving around completely freely, the disorder is increasing and the entropy will increase. Okay, so changes of state can be accompanied by changes in entropy, and the more disordered they become, the greater the entropy becomes. Also, the more gas you have, the more entropy there will be, the more disorder there will be. So if a chemical reaction, for example, some nonsense chemical reaction, or not nonsense, but made up one, if A plus B, which are both gases, turn into C, there's now less or fewer gas particles around, so it's a more ordered arrangement than it was. So whichever side of this equation has more gas in it, that's the side that will have a higher entropy. So this change here ought to have a negative entropy change because the order is increasing, the disorder is decreasing, and so the entropy is decreasing. Right, what have we got left? Oh yes, well, a quick reminder of how we used to calculate enthalpy changes all that time ago when we first learned a formula for calculating the enthalpy change if we were told the standard enthalpies of formation. Okay, we had this formula here which said that you can calculate the enthalpy change for any reaction if you know the enthalpies of formation of the products and the enthalpies of formation of the reactants. Well, the great news is that you can calculate the entropy change for any process if you know the entropies of the products and the reactants, and the formula is exactly the same. Okay, except that where we had enthalpy changes, we've now just got entropies. Right, well that's good. So let's have a quick look at an example so we can see how easy this actually is in an exam, and it should be viewed as quite an easy question if you get one of these because it's quite simple arithmetic. Calculating entropy changes, we've got this formula again which we know we can always use. Okay, and here is a reaction, okay, and we're given standard entropies of methane, of water, of oxygen, and of carbon dioxide. So we're going to say that delta S is the sum of all the entropies of the products, which will be the carbon dioxide, 214, plus 2 times water, so 2 times 70. Okay, if you add that lot up, it's on reverse, so 354. And then take away the 186 of the methane and the 2 oxygens, 2 times 205, so that's 410, 596, and we end up with a negative number of 242. Notice that this is in joules, not kilojoules like enthalpies, and this will be really important in the next film, okay? But it's important now, but it becomes even more important when you start calculating free energy changes. And notice here, sorry, that was supposed to be a negative value, wasn't it? If this is a negative value, the entropy has gone down. This suggests that things have become more ordered or less disordered. Does that make sense if you look at it here? Well, yes, because you've got 3 moles of gas here and only 1 mole of gas on the right. And we've formed some liquid, which is a much more ordered state than a gas. Okay, well, people often tell lots of scare stories about entropy, but as you can hopefully see, the sort of things you have to do with it in an IB exam aren't really all that tough. You're not going to be asked to explain what entropy is in any great detail. If you know that a system that has a high entropy has a high level of disorder, that's absolutely fine. But it's good to be able to identify the kind of systems that do have a high level of disorder. So gases have higher levels of disorder than liquids, which have, and so on. Okay, and you can calculate the entropy change for a process if you're given the entropies of the reactants and products. Hopefully it's not too confusing, but if you have got any questions or comments, then please feel free to come and ask for some help or to post a comment on YouTube.